Now it's time for 1324, Tuesday, August 2nd. And over here in week 3 homework, yesterday we made it all the way through number 16, which is more than a third of the way. And if we get 17 through about 29 or 30, that would be a pretty good stopping point for today. Okay, so now we did the easy find the mean situation, but now this is a little more difficult. How do you find the mean for a set of group data? So we have six values that are somewhere between 0.5 and 2.5. We don't have any way of knowing, is there one of them that's 0.5? Are all 6 of them 0.5? Are none of them 0.5? There's no way to know individually what each one is. So what was decided to do is 0.5 through 2.5, you go to the midpoint of that interval. Midpoint. A midpoint is when you add up the two values. Whoops, I didn't get my point. Wait a minute. Okay, so add up the two intervals, 0.5 plus 2.5. You add them up and divide by 2. Whoops, I didn't hit plus. Let me try that again. 0.5 plus 2.5 is 3. 3 divided by 2 is 1.5. In other words, 1.5 is exactly halfway between 0.5 and 2.5. And since we don't know these 6 numbers, what they are, they could literally be anything between 0.5 and 2.5. So to balance it out, we assume they're all smack dab in the middle. And in the long run, that'll even out. There may be a situation where there's more below the halfway point or more above the halfway point, but since we have no way of knowing, that's the best we can do, is just that will get you the best possible answer by assuming they're all in the middle. So halfway between 2.5 and 4.5, if you can do that in your head, halfway between 2 and 4 is 3, so 3.5. And if you can't do it in your head, 2.5 plus 4.5 equals, divided by 2, 3.5. So I'll assume those are all at 3.5, and there's 4 of them. There are 6 more that are between 4.5 and 6.5, which is halfway is 5.5. And finally, there are 8 that are halfway between 6.5 and 8.5. So that's 7.5. And then you just multiply across, because it's like I have 6 1.5s. It's like I have 6 1.5 individually. And normally you would add them all together. Well, if you have 6 of the same thing, you can multiply by 6, and that's the same as adding them separately. So this will give us a product. 1.5 times 6 is 9 exactly. 3.5 times 4 is 14 exactly. 5.5 times 6 is 33 exactly. 7.5 times 8 is 60 exactly. Add up the products. By adding up all the products, this is the same when you have individual numbers and you add them all up. If I knew every single individual number and added them all up, they would add up to 116, is what that's saying. And normally when you find a mean, you add them all up and you divide by how many there are. So adding up the products, that's the same as adding all the individual numbers. Adding the frequencies is the same as saying how many there are. 10, 16, 24. So the average or the mean, it's done in a similar way. You're just assuming that's a bunch of numbers are similar in some way. So I do a sum divided by the total. That's how we always find a mean in general. It's just the sum here is the sum of the products, and the total is the sum of the frequencies. 116 divided by 24 is 4.8333 repeating. 4.8, that's kind of near the middle of this. In fact, 4.5 is the exact middle of all the possible values. So 4.8 is close. That's generally what happens is you get close to the middle. Round to 2 decimal places, so 4.833. The third place is not high enough to add 1 to the second place. So it just stays 4.83. Okay, oh, this is the same problem. Okay, so it's the same problem, it's just a longer chart. And the intervals actually aren't so bad. The fact that you're going between 41.5 and 43.5, the halfway point of that is 42.5. And again, if you don't know that, do it like this. 41.5 plus 43.5 divided by 2, that's 42.5. So at least they made this a little better for us by doing 42.5. That's halfway between 41 and 43.5. And they're always going up by 2. 43.5 to 45.5, the halfway point is going to be 44.5. And it doesn't matter if you do these horizontally or vertically. I like to do them vertically, just lines up better, but the computer, they like to do it horizontally because it fits on a screen better. So our midpoints are going to be 42.5. Another thing about this too is once you get the first couple going, you start to see a pattern. So then you end up, you don't have to calculate them all. It would take a long time to calculate all these. But 42.5's here, this is 44.5, this will be 46.5. It keeps going up by 2, 48.5, and you're going to end at 58.5. Halfway between 57 and 59 is 58. So once you establish a pattern, then you can just keep going up by 2, up 2, up 2, up 2, up 2, up 2, and the last one should be 58.5. So frequency is how many landed in these regions, and they are given to us 2, 7, 14, 2, 7, 14, 18, 20, 15, 18, 20, 15, 17, 5, and 1. And see, I have an equal amount of categories, so everything lines up. So just go straight across and multiply, and that's called product. I'm assuming that both of these are 42.5. So if I added them up, if I took two different 42.5s and added them up, it's 85. That's the same as doing 42.5 times how many of them there are, 85. So you can add if you want, but the shortcut is, especially when there's a lot of them, whatever the value is times how many there are, that's what they would all add up to if I wrote them all down and added them up. 44.5 times 7 is 311.5. 46.5 times 14 comes out to 651 exactly. Whoops. Next one is 48.5 times 18, 873. 50.5 times 20 is 1,010. 52.5 times 15, 787.5. 54.5 times 17 is 926.5. 56.5 times 15 is 847.5. And the last one's easy because anything times 1 is itself. 58.5 times 1 is 58.5. So to get the mean, it's always the sum of the products divided by the sum of the frequencies. The sum of the products is literally like adding every single number one time, and the sum of the frequencies is dividing by how many there are. So if I do 85 plus 311.5 plus 651 plus 873 plus 1010, 787.5, 926.5, 847.5, 58.5. A lot of fives there. It's a little off screen because I was trying to read the numbers at the same time, but 5550.5. 5550.5. 2 plus 7 plus 14 plus 18 plus 20 plus 15 plus 17 plus 15 plus 1. So there was 109 numbers in the total sample here. And this actually, another point of this is it goes quicker. If I had 109 different numbers written down on a piece of paper and I needed to average them, I would have to add all 109 numbers and divide by 109. So the products help speed this process up. So 5550.5 divided by 109. And before I even press equals, if you get to where the midpoint would be, check the lowest and highest, next lowest and highest, next lowest and highest, next lowest and highest. The middle of my data is 50.5, so I'm expecting this answer to be at least somewhat close to 50.5. It very rarely equals it exactly, but 50.9, see, that's pretty close. So if you get a reasonably close answer, then you're fairly confident you did it right. If I'm expecting 50.5 and I get 72.8, something's wrong because it can't be bigger than 58. And it can't be smaller than 42, and it's most likely to be somewhere near the middle. 50.9. Round to 2 decimal places if needed, but it's not needed because it came out, oh, actually it was longer. I was already rounding. Okay, so I thought I had exactly 50.9, but no. Round to 2 decimal places, 50.922, so we're just going to keep it 50.92. Okay, and I got really close too. Oh, did I say that wrong? 50? Nope. 550. 109, yep. 550.5. Okay, I might have a slight mistake in here somewhere. So then it's hard to find the mistake is the only downside. So let me just double check these products real quick. I might have typed it wrong as I was going. And let me double check this first. 2714, 2714, 18, 20, 15, 17, 15, 1. Oh, see right there, it's not a 15. It's a 5. So that's one thing too. If you make a mistake, if they say you're wrong, make sure you wrote the problem down right. I didn't write it down right. So I had a slight brain cramp right here at this 15. It should have been a 5. So this is an easy correction. Actually, 56.5 times 5, that's what this one should have been. 56.5 times 5 should have only been 282.5. And I thought it was 847.5. 282.5. So if I do 847.5 minus 282.5, that's a difference of 565. I was 565 too high. So if I take 565 away from this, although I liked how that number came out nice, that's what the actual sum of the product should have been. So 565. So let's do 5550.5 minus 565. That way I don't have to re-add everything because that can take a while. So I actually messed up the top. The top should have been 49. 4985.5. See, one little mistake, I had a brain cramp and turned a 5 into a 15 somehow. And that was the only mistake in the whole chart. And it makes the answer quite different. Now we're all the way down to 45.73. And if you add 1 to that 3, 74. Because the next digit is an 8. 45.74, see, it's way down here. Although that seems to be off quite a bit. Seems like I should be closer to the middle than that. 56.5 times 15 and 56.5 times 5. Yeah, doesn't seem like it should be that far from the middle, but let's give it a whirl. It's still in the range, but I would expect it to be closer to 50 actually. Now I lost my answer. 45.74. Huh. So, oh, I know what's wrong. The 15 dropped to 5, so that'll make this decrease by 10. See, I could tell that wasn't right. It affected this too. There's only 99 here. I mean, yeah, 99, not 109. Because my frequencies went down by 10 too. So maybe the third time's the charm. 4985.5 divided by 99. There, now we're back to a better answer. 50.36. Make this a 6. 50.36. That seems better because it's pretty balanced. The 2 is similar to the 1. The 7 is similar to the 5. 14 and 17 are similar. 18 and 15 are similar. You should be pretty close to the middle. 50.36 makes a lot more sense. And no whammies, big bucks. There we go, finally. So I tried to, if this was a test, I would have been better off just starting all over again and spending the time to redo it all. But I tried a shortcut on finding the mistake and then trying to correct for it, and I forgot to correct both halves of it. Okay, so the median is not as heavy of a calculation. Basically what you do for the median is you figure out where would it be. So if I add all the frequencies, remember it was 99. Some of the frequencies is 99. There's 99 numbers here. So if you have an odd amount of numbers, that means there's exactly 1 in the middle. That would be the median. So if I take 1 away from 99, then there would be 1 in the middle and 98 other numbers around that. And if you divide by 2, there would be 49 small numbers, the 1 in the middle, and then 49 big numbers. That's what a median is. It's a number or numbers in the middle. So there's an equal amount above and below it. So 49 below it, 49 above it, plus it itself, that's how you get 99 numbers. So where would the 50th number be? There's the 49 small ones, and then the next one's the median. Where's the 50th number? So let's start adding from the low end. 2 plus 7, that's 9, plus 14 is 23, plus 18, now we're up to 41, plus 20, 61. So the 50th one is the median, and it's somewhere in this range where 20 is. So then again, we have no way to know exactly which one is that 50th one, but from the 41st one to the 61st one, they're all in this range. So the median's definitely in here somewhere. It's going to be somewhere between 49.5 and 51.5. Since we have no way to know it exactly, as usual, we default to the median, the midpoint of it, which is like a median. So the median of that group is the median overall, since I found which one it's in. And I already know what the answer is, but again, if you add them up and divide by 2, it's the halfway point between 49.5 and 51.5, which is 50.5. So that's just a matter of figuring out which interval does it fall into, and then, now they said 2 decimals. So do they want 50.50 and they're counting me wrong for that? No, huh. Divide the total area by 2. I did that, I added it up, divided by 2. Let's see what they say it is. 50.35. That is weird. I have to see what they're doing on that because I don't think that's right actually. Equal right and left. The mean, okay, forget that. We did that already. What are they saying about the median? They're still doing the mean here. Okay, mean, we got the mean. Okay, that's a lot of explanation for the mean. Okay, median. Oh, they're doing areas? Okay. So maybe they're using, I've seen these before and it's usually just about where the median would be, but it looks like they're using the frequencies involved with it too. 2 times 3, that is weird. Okay, so here's what I guess this is another formula for this. I haven't seen this before, but what they're doing is they're finding the area of each of those rectangles and then sum up all the areas and then divide by 2. And area is length times width. So what they've done here is they've created a rectangle that starts at 41.5 and ends at 43.5. 41.5 to 43.5. And that first one had a frequency of 2. The next one was 43.5 to 45.5 with a height of 7. The area of a rectangle is length times width. So the distances across are always 2. So if you do 2 times 2, that's 4. 7 times 2 is 14. They're doing this for all 9 categories. And it's always going to be 2 times the height, and 2 times the height, and 2 times the height. You have to do that for all 9 of them. So the easiest way to do this is look here. I'm going to do 2 times each of these numbers. 2 times the first 2 plus 2 times the first 7, or not the second number, which is 7, plus 2 times the 14, plus 2 times the 18, plus 2 times the 20, plus 2 times the 15, plus 2 times the 17, plus 2 times the 5, and 2 times the 1. This is where calculators really help. And then you divide by 2 to cut it in half, apparently. Or wait a minute, that doesn't seem right either. So I should have left that open, I guess. Total area, we got that. Divide by 2, okay. If half of the total area is 97, the median must be located. Okay, why is that true? So where is 97? See, what they're doing is they're doing what I was doing, except from the area, not just from the numbers. Although that still doesn't seem to make sense either. Half of the total area is 97. So is that the products of those? I guess here's what we gotta do. I've never seen this done this way before. That's weird. So this won't be as easy as I thought it was. So we have to go through each one of these. And this is their example. 2 times 2, I need to make a table for this because they're keeping track of the area up to that point. 2 times 2 is 4. 2 times 7 is 14. 2 times, what's the next one? 14 and 18. 2 times 18 is 36. 2 times 20 and 15. 18, 20, 15, 17, 5, and 1. Okay, so add up all of this right here. 4 plus 14 plus 28 plus 36 plus 40 plus 30 plus 34 plus 10 plus 2. The sum of all the areas is 198. They divide that by 2, which is 99. And then you go back here and you start adding this until you hit 99. 4 plus 14 plus 28 plus 36. See, I'm not at 99 yet, but plus 40. Once you've gone past 99, that's the interval you need to be in. The one that has a 20 frequency, which is here. But again, why are they getting 0.35 is the weird thing. I would still say it's 50.5. So I'm not sure why they're getting 50.35. This problem's a lot worse than I thought it was. Median must be in that one. Okay, so what are they doing to figure that out? There's all those. So m minus the beginning of the interval times the size of the interval is 97. Okay. 50.5. I got 50.5 and now they're saying it's not that. That's weird. Solve for m, so maybe I need to do that. So what does all this add up to? Then you have m minus the beginning times the size of it equals your half number. This is way more complicated than I thought it would be. So what are all those add up to? 4 plus 14 plus 28 plus 36. The ones up to that interval add up to 82. And then you do the beginning of the interval, which is, oh no, it's m minus the beginning of the interval, 49.5. M minus 49.5. And this equals your half number 99. So if I subtract 82, m minus 49.5, that would be 1799 minus 82. So see, it's still going to come out to a 0.5. I don't see how they're getting 0.35. 17 plus 49.5. Oh, that's not even close. Well, let's not waste any more time with this one. This is problem 18 of this homework, so just go ahead and skip this problem and I'll give you credit for it. I don't know why it's causing such trouble. I've seen this in a statistics class before, and you just find the location where the median would be, and then you just do the halfway point there, because we have no way to know the individual numbers. I don't get what they're doing to get that 0.35. So skip 18, and I'll mention that when I send an email out about this, but skip 18, and it's just going to take way too long to do that and figure out what's going on. There's some little rule. The one thing about statistics is that textbooks will come up with their own little rules and procedures that aren't necessarily universal in every textbook, just so that they can grade you on an assignment like this. So they're doing some kind of rule that I've just never seen before, and I don't know why it's not even coming out when I follow exactly what they're doing. Okay, so let's go back. See, it's group data is what causes some trouble, but this is a set of ungrouped sample data, ungrouped. So I have every individual number right here. Find the mean. Okay, the mean is easy if it's not group data, or even if it is, it isn't too bad. But 3 plus 4 plus 4 plus 3 plus 0 plus 1 plus 1 plus 6 plus, whoops, I lost my plus 6. I did that wrong. Let's see, 3, 4, 4, 3, 0, 1, 1, 6, and 5. Okay, plus 7. So this adds up to 34. There's 2, 4, 6, 8, 10 numbers there. So divide by 10. The mean is 3.4. And the symbol for that is right here, X bar. X bar 3.4, that's called the sample mean. Okay, so this is kind of bad because there's a lot of numbers here, but here's the way you find standard deviation. So it's a 6-step process. None of the individual steps are hard, but there's 6 of them, and then they gave us such a large sample, it's going to really take a while. So you find the mean first, which is easy. That's junior high work, 3.4. Then you have to take each number and subtract the mean. And what I'm going to do is I'm going to go ahead and do the third step at the same time, just because this list is so long. And you have to take that answer from step 2 and square it. And it can save time if you do both of these steps at the same time. So I got to take all my 10 data numbers, 3, 4, 4, 3, 0, 1, 1, 6, 5, 7. I'm going to put them down here. 3, 4, 4, 3. 0, 1, 1, 6, 5, 7. And you subtract the mean from each one of these. So I'm going to do this one at a time. Take out a calculator. 3 minus 3.4 equals negative 0.4. And then you want to immediately square it. Hit the squared key. X squared. Anything squared is positive too, so keep that in mind. 0.16, positive 0.16. So each time you're minusing 3.4, that's always the same step. 4 minus 3.4 is positive 0.6. Now hit the squared button, not the square root, the square. Square it, 0.36. And then, unfortunately, you got to do this for every single one. Now, if you get some that are the same, here's another one that's the same, then you don't have to do it in the calculator. Just rewrite the same exact answers. So that at least helps a little bit. This one's the same as the first one, negative 0.4, positive 0.16. Okay, 0 minus 3.4 is negative 3.4. 0 minus 3.4 is negative 3.4. Squared is positive 11.56. But be careful, if you do all these first and then go back and do all these second, if you type a 3.4 and hit the negative and then hit the squared button, okay, it worked here. I've seen that like on a graphing calculator, it'll mess up. If you do negative 3.4 and hit the squared button, it tells you the answer is negative because the calculator is literally not squaring the negative. And students just blindly follow what their calculator is telling them, and they're oblivious to the fact that this needs to be positive no matter what. This column needs to be positive no matter what. So I get 2 in a row of the same here at least, so whatever the first one is, the other one will be the same. 1 minus 3.4 is negative 2.4 for both of those. So once I square one of them, they'll both be the same, 5.76. 6 minus 3.4 is 2.6. Square it, 6.76. 5 minus 3.4 is going to be 1.6. 5 minus 3.4 is 1.6. Square it, 2.56. Finally, 7 minus 3.4, which will be 3.6. 3.6, square it, 12.96. So step 4, you're going to add this up. The sum of the positives is step 4. Now, if you forget this and you accidentally add these numbers up, the second column, here's a double check. If I do 0.4 negative plus 0.6 plus 0.6 minus 0.4 minus 3.4 minus 2.4 minus 2.4 plus 2.6 plus 1.6 plus 3.6. This always happens. It's always 0. The positives and negatives can't balance and cancel each other out. So this is why we're squaring. When you square anything, it gets larger, first of all, but it turns positive. So all of these are positive. There's no way this is going to add up to 0. So the first person who thought to try this, they were just doing this, and then they got 0 for an answer, and that didn't make sense. And it's all because the mean is a balancing point where the positive and negatives balance. So now let's add this up. 0.16, 0.36, 0.36, 0.16, 11.56, 5.76, 5.76, 6.76, 2.56, and 12.96. 46.4. The last two steps are each short, but this one's a little weird. So you do your sum that you just did in the last step, and you divide by what they call n minus 1. N is the size of the sample. Since we found the mean x bar was the sum of all the numbers divided by how many there were, which is called n. So we got 34 divided by 10. That's where the 3.4 came from. So now you do this big sum, 46.4, and it would be logical to divide by 10, but the rule is you divide by 9, 1 less than what you divided the mean by. 5.1555 repeating, and then that can be an answer sometimes. That's called variance. But if you go one more step, step 6, the square root of this variance, this answer is called variance. The problem is I squared them all to make them positive, but squaring things makes them bigger. 3 went up to 11, 3.6 went up to 12, 2.6 was 6. It makes them all bigger. And the opposite of a square is a square root. So square rooting brings you back to the level you were at. So the last step is the square root, not square, but square root. And then where do they want this rounded to? Round to 3 decimals. So the square root would be 2.2705. The 5 is going to add 1, 2.271. 2.271. When you square root the variance, that's called standard deviation. So there isn't any extremely hard math here. The means we've been doing since junior high. Subtracting is easy with a calculator. Squaring a number is easy with a calculator. You add all these up with a calculator. The weird part is you divide by 1 less than what you divided the mean by, and then you take a square root. Every step individually is easy. It can take a while if there's a lot of numbers, and then there's a lot of steps to know. But at least there's no hard math here. So even with a plain old calculator, you can get through this. 2.271. Okay, what proportion of measurements lie within 1 standard deviation of the mean, 2 standards, 3? Okay, so these are memorized amounts. 1 standard deviation is 68%. What proportion? Or maybe they made it from our particular data. Okay, let's do that. So here's what you do. The standard deviation was 2.271, and the mean was 3.4. So if you take the 3.4 mean, add and subtract this 2.271. So 3.4 plus, whoops, I typed that wrong. 3.4 plus 2.271 is 5.671. And 3.4 minus 2.271 is 1.129. So I'm guessing that they are asking how many of our numbers in our sample are between these two numbers. So we had, I gotta look at all the numbers again. 0 and 1 are not between that because you have to be bigger than 1.129. And you can't be bigger than 5.6, so the 6 and the 7 are out. So 1, 2, 3, 4, 5 of them are not in that range, but the other 5 are, so I guess they want 50% here. 5 out of our 10 numbers fall in that range. Okay. With 2 standard deviations, I'm guessing this is going to be 100% already because, I'll show you why, but then the other one will be 100 too. So then you do the same thing except you do 2 of these. You add this twice. That's what 2 standard deviations means. So 3.4 plus 2.271 plus 2.271. So now the upper limit is 7.9. And then you subtract 2.271 twice. And that's going to turn out to be negative because after the first one, we're already down to 1. Whoops, I put plus. 3.4 minus, it's adding on to the same problem. I got to clear this. 3.4 minus 2.271. See, that's the first answer we got. Then do it again. It's negative 1.1. So what percentage of our numbers are between negative 1 and 7.9? They're all between that. The biggest number we had was 7, I believe. Was 7 the biggest one? Yeah, 7 was the biggest number. So all 10 out of 10 are bigger than 2 standard deviations, and then of course they're all bigger than 3 as well. Would you conjecture that the histogram is approximately bell-shaped? Well, in bell-shaped, see, remember when I missed this at first? In statistics, the percentages go 68, 95, and 99.7. So I guess what this question's asking is are you close to those actual known percentages, 68, 95, 99.7? And the last 2 are, but the first one really isn't. No, because most of the data values fall between 2 and 3. That's not true though. So, okay, yes, most of the data values fall near the mean. Yep, that's true. So apparently it is yes, because this was definitely true. Most of the data values fell near the mean because after I did 1 standard deviation, I already had half of the numbers. And there wasn't anything past 2 standard deviations out. So is that right? Yeah. Okay, so bell-shaped. None of these look bell-shaped. Okay, so we had a 0 and we had 2 1s. Apparently they're grouping these together, so that could be these 3. We had no 2s, but there were 2 3s and 2 4s. 2 3s, 2 4s. And a 5, 6, and 7. So maybe it's this one. Although that doesn't look very bell-shaped. So, well, it can't be this one. It doesn't have a -2 in it. 2, 2, 2, 1, 1, 1. So I'm not sure what they're doing on these graphs, but okay. So there had to be 9, no, there were 10 numbers. 2, 4, 6, 7, 8, 9. I guess they're not doing 0. But this one's only 2, 4, 6, 8, so that didn't make sense either. I'm not sure what they're doing on that graph, but just tried that one, and you might have to guess on that. Okay, so that was weird. Okay, at least we're out of that section, which was definitely getting weird by the end of it. Okay, so this is a formula. We're about to do something called the binomial. 10.4 is binomial. And let me make a list here. In a binomial, first of all, bi means 2, like bicycle or bifocals. So there can only be 2 outcomes. Heads and tails, evens and odds, boys and girls, adults and children, things like that. If you roll a die and you try to get a 1, 2, 3, 4, 5, or 6, that's not binomial because now you have 6 outcomes. Although sometimes you can turn something that's not binomial into a binomial by doing, I want to roll a 3 or not roll a 3. Then you only have 2 outcomes, or rain and not rain. 2 outcomes. Okay, then there needs to be a set number of trials. Set number of trials, that's n. This is how many times you're going to do it. And you need to know that ahead of time. Then there's p, the probability of success. These 2 are usually told to you in every problem. There's a q that they never tell you, or usually they don't, and you get this by doing 1 minus p. They're complements of each other. It's like rain and no rain. If there's an 80% chance of rain, there's a 1 minus 0.8, 0.20, 20% chance it won't rain. So this is the probability of failure. Now, success and failure doesn't mean good and bad. Success just means the one you're interested in. So if I'm trying to get heads on a coin, then the heads are successes and the tails are failure, not that there's good or bad anything to that. And then x is the number of successes you're hoping for. So I could flip a coin 10 times. That would be n, 10. Coins come up heads 50% of the time. 1 minus 50% is 50%, so tails come up 50% of the time. And maybe I want to try to get the probability of 7 heads out of 10. That would be a binomial. The formula for it is n combination x times p to the x power times q to the n minus x power. And that's what they put right there. And they actually told me n, x, and p. Notice they didn't tell me q. They never tell you that one. They think you know the rule to find that. Okay, so I'm told that n is 5, x is 2, and p is 1/2. So I'm going to do 5 combination 2. 5 combination 2. For 1/2, you can use 0.5 for that. 0.5 is easier to work with. 0.5 for p. And then see this x here is the same as that x right there. So that 2 gets repeated right there. And then you could quickly figure out q yourself by doing 1 minus p. But if one of them's 0.5, that's when they're both 0.5. That's the only time they're both the same. So then this is 0.5, and then you do n minus x which would be 5 minus 2. So 5 combination 2, you figure that out first, and there's an easy way to calculate that. You start at 5, you decrease by 1 over and over potentially until you have this many numbers. So I need to stop after 2 numbers. 5 and 4, I've got 2 numbers. And then you divide by, starting with the 2, all the way down to 1. And you can either say this is 20 divided by 2, which equals 10, or you can divide the 2 into the 4 and say 5 times 2 is 10, which is usually easier. So I've got 10 times 0.5 squared. This equals 10. Here's 0.5 squared. And then it helps on this last part if you subtract that in your head or on your calculator ahead of time. 5 minus 2 is 3. So make that 0.5 to the 3. Now you can type it all in a calculator. 10 times 0.5, here's my exponent button, raised to the second, times 0.5 raised to the third. And sometimes these two numbers are usually different. They're just, this is the one time they're the same. So there's a 0.3125 probability of this happening. If you flip 5 coins, there's a 31% chance you'll get 2 heads, is what that's saying. Round to 3 decimals, so I'd have to bump that up from 3125. You have to add 1 to the 2 and make it 313. A fair coin is tossed 4 times. What's the probability of getting at least 3 tails? So now tails is what we're interested in. So now we're only flipping the coin 4 times. Coins come up heads or tails 50% of the time, so that means both P and Q are 0.5 again. Now the only issue is X isn't exactly 3, it's at least 3. At least means greater than or equal to. And I only go to 4, so greater than or equal to 3 in this situation means 3 or 4. So you just have to do this twice and you add the answers together. So again, it's n combination x, p to the x, q to the n minus x. That's the formula. So I need to do 4 combination 3, 0.5 to the 3. Remember that those two 3's always match. And then there's another 0.5 to the 4 minus 3. 4 combination 3 is figured out by doing 4, 3, 2, stop after 3 numbers, and then the bottom's 3 down to 1. And there's always an equal amount of numbers in the top and the bottom. So if you have like 6 numbers on the top and only 5 in the bottom, you did something wrong. And this is nice because the 3, 2 cancels the 3, 2. The answer is 4 divided by 1, which is 4. So that's 4. I just rewrite the middle one. And then when you write the last one, do the subtraction in your head. 4 minus 3 is 1. Now you're able to type it all in at once. 4 times 0.5 raised to the third times 0.5 raised to the first. That answers exactly 0.25. So you got to do this again, but it's not maybe as bad as it might seem. So 4 combination 4 this time, but this is the key, is the x is changing. The x is changing from 3 to 4. That's all that's changing. And you remember these two numbers always match each other. So the combination's not going to change. The 0.5s aren't going to change. But if there's a 4 here, there needs to be a 4 there no matter what. And the other thing is the 2 exponents add up to the n. 3 plus 1 is 4. So I could just say to myself, 4 plus what's going to get me this front 4? 4 plus 0 gets you 4. And the other way of thinking about this is saying I want 3 tails and 1 head. So if you bump the tails up from 3 to 4, the heads have to go down from 1 to 0. 4 combination 4, let me do it here. 4 combination 4, so you start at the front number, you decrease by 1 until you have this many numbers. So 1, 2, 3, 4. And then you start with this number and go all the way down to 1 in the bottom. But the entire top cancels the entire bottom. Anything divided by itself is 1. So if you ever get something combination the same something, the answer is just automatically 1. This answer is 1. Anything to the 0 power is 1. And anything times 1 is itself. So the 1s don't matter if there's still other stuff multiplied here. So the answer to this part will be whatever 0.5 to the 4th power is. 0.5 to the 4th power is 0.625. So I have to do, when it's at least 3, you have to do the case of 3 and the case of 4, and you add your answers together. 0.625 plus 0.25. And that's 3125 again by coincidence, but it does say type of fraction. Okay, that's bad because you're probably not going to know what fraction this is. Well, here's the way you do it. The only way you can do it. It literally means if you have 0.3125 tenths, hundredths, thousandths, 10,000ths, it literally means that number divided by 10,000. Now, does it say simplified fraction? It does say simplify, okay. So those both definitely divide by 5. 3125 divides by 5, 625 times. If you end with a 0 or 5, you divide by 5. 10,000 divided by 5. This problem's only going to be messy because they won't take a decimal answer apparently. 2,000. They still end with 5 and 0, so they divide by 5 again. Divide by 5. 400 for the bottom. 625 divided by 5 is 125. They still divide by 5. 25 for that top. 400 divided by 5 is 80. Those still divide by 5. 80 divided by 5 is 16. That does not divide by 5. 25 divided by 5 is 5, so that's as far as it's going to go. So it's a little painful to do that, but only because they asked for a fraction. If they would have just said, give me a decimal, we would have been fine. 5 divided by 16. Okay, this will be better. A fair coin is tossed 6 times, so there's n. You know you're going to do it 6 times. We know heads and tails are both 0.5. Now we want no heads. We want x to be 0. And just 0, not at least 0. At most 0 is just only 0. So these problems aren't so bad if you just have one case to do. So we're up to number 22. 22's got n is 6. And if it's about coins, then automatically both P and Q are 0.5. We might see one where that's not true. And then we want exactly 6. Exactly 0. No heads or no tails means exactly 0. N combination x, P to the x, and Q to the n minus x. So 6 combination 0, 0.5 to the 0. Remember, these two have to match each other. And then 0.5 to the 6 minus 0. So whether you do, if you ever do a 6 combination 6, I already told you that's automatically 1. It's also automatically 1 if the last number is a 0. In fact, a combination can never equal 0. The lowest it can be is 1. So this is 1, and anything to the 0 power is 1. And again, we're multiplying, and there's something left here, so then you can ignore these ones. And 6 minus 0 is 6, so whatever 0.5 to the 6 is, that'll be the answer unless they want a fraction. 0.15625. Hopefully they don't want a fraction. That'll take a while. The integer simplified fraction. Okay. So what if I do put 0.5625? Yeah, it's equal to the correct answer, but it's not in the correct form. So unfortunately, they're doing fractions here. So here's what we actually have to do then is with these 1/2, there is an easier way to do this because these two parts are 1. I need to change this back to a fraction is what's going on here. So instead of doing 0.5 to the 6th power, we need to do 1/2 to the 6th power. And then when you have a fraction to a power, you can do each half. So I need to do 1 to the 6th power, and 1 to any power is 1. And then I need to do 2 to the 6th power, which is 64. So this is 1 over 64, and then that way you wouldn't have to do this big mess that I did here. See, we could have done that on this problem. I could have wrote 1. Was this the one that came out that way? No, that was a different one. Where was that one? Oh yeah, we had to add these together. Okay. So yeah, so that wouldn't be as easy. I guess there wasn't an easier way to do this one. But since we're just doing this one case and these two 1s are gone, then you can do that. 1 over 64. And remember what I got for a decimal? I had 0.5 to the 6th power. I got this decimal right here. So 1 divided by 64 should equal that same decimal. 1 divided by 64. See how it's the same decimal? And I don't know why they're being picky and wanting a fraction when the decimal's equivalent, but 1 over 64. A fair die is rolled 4 times. What's the probability of getting no 6s? So now they're going back to decimals, at least in the answer. What is the probability of obtaining no 6s? So a 6 is considered the success, and not a 6 is the failure. And we want no 6s, so in other words, x has to be 0 again. We have 4 rolls of the dice, so that's n. The only difference on this problem 23 is it's not 0.5 for P and Q. So we're rolling a die 4 times. We want no 6s, so that means x is 0, exactly 0. But a 6 on a die, we have to figure out what's the probability of getting a 6 on a single die, and it's literally 1 out of 6. And then the probability of not getting a 6, which is Q. So this is P. And then you do 1 minus that to get Q. And the trick for that is change the 1 to be 6 over 6. 6 over 6 minus 1 over 6 is 5 over 6. So I'm going to do n combination x, 4 combination 0, 1/6 to the 0 power. That'll be nice because it'll go away. And then 5/6 to the 4 minus 0 power. 6 combination 0 is automatically 1. Anything to the 0 power is automatically 1. And 4 minus 0 is 4. So if I just do 5 to the 4th and 6 to the 4th, I'll actually get the fraction. This time the fraction's easier. 5 to the 4th is 625. 6 to the 4th is 1296. Although reducing that fraction would be hard, so luckily they're going to take a decimal here. There it goes. 625 divided by 1296. They said 3 decimals, I think. Yeah, 3 decimals. So 4822, you can keep that 482. 482. Okay, if a baseball player has a batting average of 280, that's your P, that's your probability of success. What is the probability they will get a hit in their next 4 times at bat? Oh, to get the number of hits in their next 4 at bats. So first they want exactly 2. That's the easy case. So we got 4 at bats, that's my set number of trials. The player gets a hit 0.28 of the time. So therefore Q is 1 minus that. 1 minus 0.28 is 0.72. So they get a hit 28% of the time and they make an out 72% of the time. And part A is the easy part. They want exactly 2. So N combination X, P to the X power, notice the double 2 right there, and then Q to the N minus X. 4 combination 2, we got to figure that out off to the side somewhere. So start with 4, decrease by 1 until you have 2 numbers, and divide by 2 down to 1. And this will cancel, so 2 times 3 is 6. 4 combination 2 is 6. 0.28 squared doesn't go away or anything. And then 0.72, we need to do this 4 minus 2 and make that a 2. Now I can just type all this in, multiply together. So 6 times 0.28 raised to the second power times 0.72 raised to the second power. So there's, how many decimals do they want? 3 decimals. There's a 244. You got to change this 3 to a 4. 244 probability of getting 2 out of 4 hits. 244. That's part A. Now, at least 2 means 2 and higher. Now, although n's only 4 at least, if n was like 20, that would take a long time. But part B wants at least 2, which means greater than or equal to 2, which really means 2, 3, and 4 in this case. And we've already done 2. So we just have to do this again for 3 and 4, and it's not as bad as it seems, because we can take the one we did already and just adjust from it. So the only thing that's going to change is look right here and make the changes right there. It's only this 2 that's going to change in all 3 slots. It affects everything, but it's an easy change. So I'm changing the 2 to a 3 first. I want to change the 2 to a 3. Everything else that I didn't circle stays the same. 4 combination 3. 0.28 to the 3, because those 2 definitely have to match. And then 0.72, see if you can do this in your head. 4 minus 3. 4 minus 3, that's going to be a 1. And then when we do this one, it's going to be 4 combination 4. Now change the 3 to a 4. 0.28 to the 4, so those match. And 0.72 to the literally 4 minus 4, or 0. And notice the sum of the exponents. 2 plus 2 is 4. 3 plus 1 is 4. 4 plus 0 is 4. And this is a baseball player trying to get hits or make outs. The first case, he or she got 2 hits and 2 outs. Now it's 3 hits and 1 out, and then finally 4 hits and no outs. So every time one of those goes up 1, the other one has to go down 1, because the player's only batting 4 times. So 4 combination 4, that's easy. That's 1. Anything to the 0 power is 1. So the last answer is just the middle part, 0.28 to the 4th power. 0.28 to the 4th power. And they want 3 decimals, so I'll just make that 006. This answer is 0, 0, 6. And we already did this case, so all I need is this case. And I just got to figure out 4 combination 3. That would be start at 4, decrease by 1 until you have 3 numbers, and then do 3, 2, 1 in the bottom. The 3 2's cancel, so that's 4. So this part is 4. I need to do 4 times 0.28 to the third times 0.72 to the first to get this answer. 4 times, I know you can't see it, but 4 times 0.28 raised to the third power times 0.72 raised to the first power. And round to 3 places, 063. So the chance of at least 2 hits is the chance of 2 hits plus 3 hits plus 4 hits. Any of those are at least 2. So just add those 3 decimals together. 244 plus 063 plus 006. There's about a 31% chance this player will get 2 or more hits in a game. But that means there's a 69% chance they're going to get less than 2. 313. The at least and the at most, they're not hard. They just are a little annoying because you got to do multiple cases. The exactly's are the nice one. You just have to do 1 case. Okay, at least this is faster. So it's easy to find the mean and the standard deviation of a random variable that's binomial, or what they call Bernoulli. Bernoulli was the mathematician who worked with the binomial distribution. So remember when we found the mean and the standard deviation of that set of 10 numbers, and it took a long time even though it wasn't extremely hard? If you have a binomial case, it's a whole lot easier to get the mean and the standard deviation. The mean of a binomial is simply n times p, the 2 numbers they usually give you in the problem. There's 20 trials here, 20 Bernoulli trials, and each has a probability of 0.65. That's n and p, literally. 20 times 0.65. This is the mean of this problem. 20 times 0.65 is 13. The standard deviation of a binomial is square root of NPQ. 20 times 0.65, and then we got to figure out Q. Remember, they never tell you Q. So if P is 0.65, Q is 1 minus that. You just figure that out ahead of time first. 0.35. So the standard deviation would be 20 times 0.65 times 0.35, and then take the square root. And how many decimals? This one wanted an integer, 13. And then 3 decimals for this standard deviation, 2.133. Okay, what's the probability the number of successes lies within 1 standard deviation of the mean? Find the probability the number of successes lies within 1 standard deviation of the mean. Okay, so I know what they mean by 1 standard deviation of the mean. So once you know the mean is 13, we did this a few problems ago. Take the mean, add the standard deviation, 2.133. And subtract the standard deviation. This is what it means to be within 1 standard deviation of the mean. 13 plus 2.133, so if you're 15.133, that's the upper limit. And then 13 minus 2.133 is 10.867. So they want, what's the probability that you would get somewhere between 10.8 and 15.1 successes? Now, I don't know if that means they want me to physically calculate every single one of those cases or not. Probability number of successes lies in that range. So let me try this real quick and see if this is what they want. A binomial, if we did 20.65, if we did 15, and then, whoops, and then if we do, what's the other number? 15, I guess you'd round that up to 11. .376. Let's see if this is the answer. If not, then I gotta check what they actually want here. Okay, 644. No, okay. A sum of two or more probabilities. Okay, we did do that. Let's see what I don't know what they're doing on this part B. See, there's the mean and standard deviation. We did that already. The number of successes is an event with more than one outcome. Yeah, we know that. We got the interval. Let's see, that's what I was afraid of. Okay, so here's the bad news on this one. So what they're saying here is that round this to 11, round this to 15. They want me to find all the probabilities between 11 and 15, which unfortunately is a very long list for the process of doing this. 11, 12, although if you change them up problem to problem, it's doable, but it's still kind of long with 5 different cases here. So n was 20, 20 combination 11, 0.65 to the 11, and 0.35 to the 20 minus 11. And then it's going to take a long time to do all these combinations too. So let me just put in what this is going to be. If you do the first one, that's going to turn out to be 116 if you actually took the time to do all that. The next one would be 20 combination 12, 0.65 to the 12, and 0.35. See, this 20 minus 11 here was 9. So this is going to increase by 1 to 12. This will decrease by 1 to 8. And if you do that, it'll turn out to be 161 for the answer. 161. Oops, I bumped the camera. Then you go to 20 combination 13. I can't believe they're making us do such a really long one, and I'm cheating a little by doing these in one step instead of the way they're meant to be done. 7, 20.65 and 7. This one's 004. Next would be 20 combination 14. 0.65 to the 14, and then the 0.35, that's going to drop to 6 next. This one, I did that last one wrong way. It was 12. Then we were doing 13. Yeah, this one was wrong. 0.184. And then this one is 14, 171. And then finally 20 combination 15, 0.65 to the 15, 0.35 to the 5. See, this part isn't so bad. Doing this isn't bad because all that's happening is this is going up 1. And the exponent always matches here. And then this exponent goes down by 1. So these are easy to write when there's a bunch of cases, but they're not easy to calculate when there's a bunch of cases. So this last case would be 127, and then you just have to add all these together. 116 plus 161 plus 184 plus 171 plus 127 is 759. 759. Yeah, so unfortunately there's no shortcut to that one. But the good thing about this problem is the part A. The part A is very valuable to know. The part B is just kind of painful to do. So that's another one. You can skip that if you want, and I'll give you credit for it because it's just going to take too long to do. But it is doable if you did all this. That would take probably an average student 30 minutes to do all this, just to do the part B, and we've already done some cases like it. But I can't delete the part D from the homework, so unfortunately, in order to learn the mean part, there was no other way to do that. Okay, so this one doesn't seem so bad. This is not looking good. And then I know what's happening there. There's a shortcut to that one. Okay, this one's better. This is how that 25 should have gone. The probability that a marriage will end in divorce within 10 years is 0.25. That's P. What are the mean and standard deviation for a binomial involving 4,000 marriages? This is an easy problem, number 20. What are we on, 29? 29. So 4,000